All right, so we're understanding this unit is the function analysis unit, F analysis. F analysis. So we're understanding what F looks like, the shape of F, by looking at derivatives, okay? And we're going to end up looking at a second derivative today. The question is why? And what does the second derivative tell us? So I'm going to first start with this. If F prime is increasing, what does that mean for the graph of F? Now, F prime increasing, what does it mean to increase? It means you're going up. So let me just write down some values that are increasing. -3, -2, -1, 0, 1, 2, 3. This is increasing in its values, okay? You can go from larger negatives to less negatives, negatives to 0 to positives, positives to more positive. That's what it means to increase in its values. Now, what would a graph of F look like if its tangent slopes at, say, these locations were -3, -2, -1, 0, 1, 2, and 3? Like, I know a tangent slope of 0 is like a horizontal tangent. So it's like maybe like that or something right around there. But you got to tell me what's going on to the left and to the right. So sketch F. If its tangent slopes go from -3 to -2 to -1 to 0 to 1 to 2 to 3. So tangent slopes are -3, -2, -1, 0, 1, 2, 3. Right? We can see F would look like this. Its tangent slopes are increasing. More negative, less negative, less negative, 0. A little bit positive, more positive, right? Does that make sense? Okay. Now, discuss with your neighbors. When something is increasing, what does that mean? Recall last lesson. When something is increasing, what does that mean in terms of like calculus concepts? Go. In terms of calculus concepts, if something is increasing, what does that mean? This is very important. You take good notes, we'll find out. Beautiful. Going back to Unit 3, Lesson 2, the second page. Something is increasing when its derivative is positive. Something is decreasing when its derivative is negative. Very, very, very important. If I know a tangent slope is positive, that means I know the function's going up. If I know a tangent slope is negative, that means the function's going down. So if F prime is increasing, which it is, F prime is increasing, that means F prime's prime, or F double prime, is positive. So if F double prime is positive, F prime must be increasing. If F prime is increasing, my function must look like this. That's the case for the entire function. What would it look like if F prime was decreasing? If F prime went from 3 to 2 to 1 to 0 to -1 to -2 to -3. These are decreasing values. What does F look like if F prime is decreasing? Go ahead and just sketch those like tangent slopes, and then you'll be able to kind of like fit a function inside those slopes? Gene, no packet.
Yes, I was.
I always have extras if you're ever absent.
Thank you.
So if my tangent slopes are 3, then 2, then 1, then 0, then -1, then -2, then -3, you can see my function has to look like that. Right? Okay. Well, if f prime is decreasing, like we said last class, its derivative, f prime's prime, which is f double prime, must be negative. Okay? What this is helping us discover is that a sign of a second derivative will tell us like the acceleration of a function or the concavity of a function. Because this graph up here is the graph of something that we call concave up, similar to the graph of like x squared. This function is concave down. If a function is concave up, this is f and this is f, its derivative is increasing from negatives to less negatives, negatives to zeros to positives, positives to more positives. And if its derivative is increasing, that means the second derivative is positive. If f is concave down, the tangent slopes end up decreasing, which means its derivative must be negative or the second derivative must be negative. Here is a graph of a function that has no concavity. Discuss with your neighbors what is going on with its f primes. They're the same everywhere. They are constant. Now discuss with your neighbor, if values are constant, what does that say about its derivative? Or if f prime is constant, what does that say? Its derivative is 0. Okay? Now, these graphs that you're going to see, are actually this graph that you're going to see, is something we need to be comfortable with. Shh. Oh, I just had it. Because not all functions will be concave up or concave down everywhere. Here is an example of a function that changes in its concavity. This first piece of the function is concave up. Now I'm going to use CC up to represent concave up without having to write concave up. Then we hit a point and we can see between these next 2 points, we are now concave down. Then we can see this piece of the graph, f is concave up, going back to switching to concave down, and then back to being concave up. So the concavity of a function may change. You're not always going to be concave up like x squared. You're always going to be concave down. Well, we will know the sign of the second derivative of f. If f is concave up, its second derivative is positive. If f is concave down, its second derivative is negative. Positive. Negative. Positive. Well, if we change from positive to negative or negative to positive, what do you think is going on at these points? Discuss with your neighbor. If you change from positives to negatives or negatives to positives, what do you have to have between the positives and the negatives and the negatives and the positives? A zero or an undefined. So in this case, for all of these situations there, f double prime must be 0 or undefined. That's how we switch from positives to negatives. Now these points are important points. We call these points of inflection for f. POIs for short. Okay? Okay. Now, the following graphs, I'm going to skip because it's pretty much the same thing as what we already talked about. We're just going to go ahead and just state what we discovered and what we know now. A function is concave up when its second derivative is positive. I want to say f, but I don't want to say f. I'm going to stick with something. Something is concave up when its second derivative is positive. Something is concave down when its second derivative is negative. No concavity if its second derivative equals 0. Points of inflection for f are when the second derivative changes sign, when the concavity changes for a function. That's when the second derivative will change sign. So if I said f, when does f have a point of inflection? They will always occur when our second derivative is 0 or undefined. But not every single 0 or every single undefined point will be a point of inflection, similar to maxes and mins. Now, not every single first derivative equal to 0, which we call the critical point, gave us a max. But these are where signs change it. We have to change through a 0 from positives to negatives, or through an undefined value from positives to negatives. Okay? So, thinking about sign analysis, and now we're doing understanding signs of second derivatives. If I asked you, here's a function, tell me when this function is concave up, tell me when this function is concave down, and tell me when this function has points of inflection. You, right now, should be able to discuss with your neighbors what you should do. Go. We should all, and most of us are doing this, be thinking to ourselves, oh, it's just the same thing as what we did last class, sign analysis, but with our second derivative. We should be thinking, oh, I need to end up with something like this, which is what we did to kind of analyze our signs, but instead of f prime, I'm going to analyze the signs of f double prime. All right, so let's do this. We're going to do a second derivative sign analysis, which is great because we've already done sign analysis for first derivatives, so we're comfortable with analyzing signs of things. When are things positive? When are things negative? What is important about sign analyses? are when our signs could change. Our signs could change at zeros or when things are undefined. I don't have to worry about when things are undefined because I don't have a denominator. I just need to worry about when the second derivative equals 0. These are possible sign change points. So I will factor to solve. I get 0 and 2. And then I remember that if I just plug in test points, as long as I've exhausted all of my zeros and all of my undefineds, I know that using one test point in an interval will give me the signs of all of the points in my interval. For example, plug in 3, 12 times 3, positive, 3 minus 2, positive, positive times a positive. It's the same thing that you have done, that you have practiced, that you have quizzed on, just with the second derivative. So plug in 1. Plug in -1. And I get this. However, what we're used to doing underneath this is like drawing arrows, denoting if f is increasing or if f is decreasing. But the signs of f double prime, yes, tells me if f prime is going up or going down. But actually, that's not what I want. I want to determine the concavity of f. So instead of talking about f prime going up and going down, I'm just going to say f, the concavity of f. F is concave up. F is concave down. F is concave up. So yes, if f double prime is positive, that means f prime values are increasing, but the question is not about when is f prime increasing or decreasing. The question is about the concavity of f. So f, x to the fourth minus 4x cubed, is concave up from -infinity to 0 and from 2 to infinity. F is concave down from 0 to 2. X equals 0 and 2 are points of inflection. It's nice to see our work being successful. If I graph the original function, x to the fourth minus 4x cubed, I will see concave up until 0, concave down. Let's see, we have a min down there, so let's pop us down to -30. There we go. Concave up until 0, concave down until a point of inflection at 2, concave up after 2. There you go. I can see the shape by graphing. Okay? Now, let's look at x to the fourth. And let's compare x to the fourth to x squared. Okay? The second derivative of x to the fourth is 0. Does this mean y equals x to the fourth has a point of inflection at x equals 0? A common mistake made with students, I don't know why, is that they forget to do the sign analysis of the second derivative, and they just like find the zeros and they say those must be points of inflection. But I wanted to put 2 examples in a row to make sure you don't do that. If you found the second derivative of x to the fourth, you see it's 12x squared. And at 0, we get 0. So this is a potential location where the signs of f double prime might change. But we can see, and it's pretty obvious since it's x squared, that if I plugged in test points into f double prime, that to the right of 0 we're positive and to the left of 0 we are positive. That means f is concave up, then concave up. But there's a point at 0 where we have a 0, which means we have no concavity. That's interesting. How does that happen? I'll show you in just a second. What does x to the fourth look like? Does anybody know what x to the fourth looks like? It's not w. If I expanded it out and there's more kind of zeros, then yes, it would be something with 3 changes. But since it's just x to the fourth, it actually looks similar to a function we know. It's like a parabola. It's like x squared. Let's look at x squared really quick. Its first derivative, 2x. Its second derivative is 2. If x squared second derivative is 2, what does that tell me about x squared? Its concavity is constant, and what kind of concavity do we have? Concave up. This is very important, and a lot of people miss this because they are confused about this constant. 2 is a positive number, right? So for y equals x squared, its second derivative is positive everywhere. This graph is concave up everywhere. But x to the fourth actually isn't concave up everywhere. At 0, it has no concavity. Let's just compare the two functions really quickly. If you looked at x squared, it concave up, just like the graph of something that's concave up that we were introduced with. Watch how x to the fourth ends up being a little bit flatter and a little bit steeper. It's concave up until 0. It flattens out so much at 0 that there's actually a point. See how it flattens out? It almost looks like it's coming into turning into a straight line. It actually will flatten out so much at 0 that they will have no concavity at 0 versus the x squared, which is concave up everywhere. So that's interesting. That just shows you that there can be situations where our second derivative equals 0, but would not be a point of inflection. I would say for f of x equals x to the fourth, f is concave up from negative infinity to 0 and from 0 to infinity, but I would not include 0. X equals 0, we have no concavity. But it's not a point of inflection. Okay? You will see that happening as well for x to the fifth plus 5x to the fourth. There will be a location that ends up not being a point of inflection, even though the second derivative will equal 0. Go ahead and do the sign analysis for x to the fifth plus 5x to the fourth. 5x to the fourth. So at -1, -1 squared is a positive. -1 plus 3 is a positive. At 1, I also have a positive times a positive. At -4, that's when the negative value squared is a positive, but -4 plus 3 is a negative. I only change signs at x equals -3. So the function f is concave down, then concave up, then flattening out enough to have no concavity, and then continuing on to be concave up. So we only have one point of inflection. X equals -3 is our point of inflection. Okay, and let's just go ahead and look at that just so we can see that kind of x to the 4th situation for x to the 5th plus 5x to the 4th. Well, you can see at 0, it's the same thing as what we saw. Let's just go back to Zoom Standard. We'll see concave down until -3, and at -3 it changes to being concave up, flattens out significantly at 0, and then concave up from there. If I zoomed out, we'd be able to see that point of inflection a little bit clearer. Okay? All right, cos x minus 1/4 x squared from 0 to 2 pi. Examine the concavity for this function. We need to be comfortable with trig functions. We need to be able to solve this equation. I'd add a half, I'd multiply by -1 or divide by -1 to get cos x equals -1/2. I am thinking about when my horizontal is just -1/2. That's going to be at the pi/3s in the second and the third quadrants. So x is 2 pi/3 and 4 pi/3, leaving it there. I have an endpoint, 0 and 2 pi. However, if I continue to go around my circle, the next pi/3 I would get to, if this is 3 pi, which is 6 pi/3, what am I thinking? 9 pi/3s, this would be 8 pi/3. I kept going around the circle, like the next one I would get to would be 8 pi/3. So 2 pi is actually a possible test point if we wanted it to be. Same with 0. If I went around my circle to the left, not to the left, but like clockwise, I would get the next solution would be at -4 pi/3. That is telling me that 0 can be used as a test point. 2 pi can be used as a test point. Sometimes we'll want to use those values because they'll be easy to work with. If you're not comfortable using those values, you can use something as easy as pi/2. You could use something like 3 pi/2. It doesn't matter. And those are the values that I would be using. The extremes. Now, make sure you go back to your second derivative. It's negative cos x minus 1/2. Pick values that work easily. Maybe pi/2, pi, 3 pi/2, maybe use 2 pi, maybe use 0, doesn't matter. My pi/2s actually are very easy to work with because I know what the cosine of pi/2 is. It's 0. So this would be 0 minus 1/2. That's a negative. 3 pi/2. The cosine of 3 pi/2 is 0. Again, that's 0 minus 1/2. That's easy. That's negative. Pi, the cosine of pi is -1, so I'd have a minus -1 minus a half. That's +1 minus a half. That is confirmation of the changing of my signs. So this cos x minus 1/4 x squared turns out is concave down until 2 pi over 3, concave up till 4 pi over 3, then concave down. All right, I'll just leave it there. Yes. Don't go to infinity. Definitely don't go infinity, because we know that's not going to be true, because I do have another critical point at like 8 pi over 3. So if I kept saying we were concave down everywhere, that'd be wrong. So yes, make sure you do stop at 2 pi and stop at 0 for the analysis of your concavity. Okay? Might as well write it down. Don't go to infinity. Say from 0, and we actually would include 0, because we would have a negative there, to 2 pi over 3, and from 4 pi over 3 to 2 pi, but we would include 2 pi. We are concave down, and then between but not including our two values, we'd be concave up. The next question is similar, so I'm going to change it up a little bit. Just want us to be careful, and this leads us into the next type of problem when I'm giving you the graph. Make sure you look and you know what's given to you. If you're asked when is f concave down, but you're given f prime, don't take two derivatives. You're already given the first derivative. You would just take the derivative once to get the second derivative. Do your sign analysis from there. We can quickly do this, but mostly the importance of this example is understanding if you're just given f prime, you don't have to take the derivative twice, just once. I plug in 3, -9, +1, plug in 1, -3, -1, plug in -1, +3, -3. So f is concave down to the left of 0 to the right of 2. Okay, bringing us to our friend, the graph of f prime. I can give you the graph of f prime and ask you about the concavity of f. Now, if you look at this function f prime and you're like, oh, it's concave down until 1, concave up after 1, points of inflection x equals 1. Nope, you're not thinking about it the right way. The signs of what tell me the concavity of f? The signs of what tell me the concavity of f? F double prime. Okay, so I need the signs of f double prime. Now, some of you already answered this and know what to do. Some of you don't. If I am given the graph of f prime, what will give me the signs of f double prime? Discuss this with your neighbors. Wow. Many of you are all over this. The slopes of f prime, the derivatives of f prime, give you the values or the signs of f double prime. We will, on top of f prime, sketch tangent slopes, positives, less positive, but whatever, we're just going to say it's positive. 0. A little bit negative, more negative, who cares? We just care that it's negative. Less negative, 0. Positive, more positive, right? So we have a positive signs until -1 where we have a 0. We have negative signs until 0. We have positive signs. Now, again, f prime is increasing. We talked about if something is going up, its tangent slopes are positive. So we are going up until -1. We are going down until 2. We are going up after 2. There's another way to be able to get these signs. But after doing this, we can tell that f is concave up, then concave down, then concave up. Points of inflection are at x equals -1 and 0. All right. Again, graph of f prime. What are the inflection points of f? When is f concave down? I want a couple points there, but you'll find that they don't matter. Go ahead, do it, check with your neighbor. The tangent slopes of f prime are positive until here, where they're 0, and then they are negative. Positive, 0 at 0, negative after that. F is concave up to the left of 0, concave down to the right of 0. Points of inflection at 0, from 0 to infinity, or x is bigger than 0. Are when we are concave down, not including 0. Okay? People get afraid of sharp points and jumps. Don't be afraid. If you are asked questions about concavity, you look at slopes of f prime to give you signs of f double prime. Ready? Positive, 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 positive. Until I get to 1. What would we say is the value for f double prime at 1? Undefined is correct. It is not 0. Because it's a sharp point. Now people freak out. They're like, oh, that must mean it can't be a point of inflection. Well, look at the slopes. Negative, 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 negative. They are negative until 3. That means f is concave up and concave down. You have an undefined value at 1. Who cares? You change signs. X equals 1 is a point of inflection. To the right of 3, positive, 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 positive. What's going on at 3? Well, I don't have a defined tangent slope at 3 as well. But I would still say that 3 is also a point of inflection. Okay? What we'll find, and next class what we will be doing, is we'll be combining the analysis of the signs of f prime with the signs of f double prime to understand what the graph of f might look like. And I'll do this kind of quickly, and you'll do this in the future. F prime is negative, while f double prime is positive. We are decreasing concave up until -1. Then we're increasing concave up until 1. Then we are increasing concave down until 2. This is a situation where we might have a vertical tangent. So this sharp point could just be a situation where we might be just going vertically. Not necessarily vertical, but it's okay if we just understand what the graph would look like. Then at 2, we are decreasing concave down. And then at 3, we jump from decreasing concave down to increasing concave up. We would end up going like that. We have a sharp point. We go from concave down to concave up. We'll go from decreasing to increasing very quickly. Like throwing those all together is what we will be expected to do next class. Okay. Again, understand what you have. You were given the graph of f prime. Now, this is the graph of f double prime. F double prime. You converse with your neighbors. Tell me, when does f have a point of inflection? And when is f concave down? Are you ready for everything else? Like that? Do you remember? Yes. Do you remember stat edit to put in data?
No.
Okay, you need to go back and review this then before you take the test, or else you'll bomb things. How's this different? Well, now, the signs of f double prime are just given to us. Here are positive values of f double prime. Positive values. Here are negative values of f double prime. Positives, negatives, positives. So when I'm given the graph of f double prime, it's kind of like I was giving you the graph of f prime and you tell me where f has maxes and mins. You look at the values. F has a point of inflection at -1 and 1. F is concave down between -1 and 1. See how that's different? This is how they up the level of difficulty with questions here of f double prime is they can give you a bunch of stuff and you really have to be able to interpret things. Okay? So given f double prime, look at the values of f double prime to understand the signs of f double prime. Okay, one more. This is the graph of f. When is f double prime 0? There's a couple ways to do this. A tricky way and an easy way. Now, typically when they give you the graph of f, they'll tell you, hey, this has got a max at x equals 0, it's got a min at 2, and a point of inflection at 1. Okay, so that would be given to you. The tricky way to do this would be to like sketch f prime and then sketch f double prime. But that is a lot harder than the other way, which is taking this and translating it into what it tells us about f. Discuss with your neighbor. If f double prime is negative, what does that tell us about f? The sign of a second derivative tells me the concavity of the function. If f double prime is negative, that tells me f prime is decreasing. F double prime is negative, f is concave down. This is where it gets tricky. Because like, yeah, f double prime is negative, f prime is decreasing, sure. That's one thing it tells us. But it also tells us f is concave down. All three are synonymous. If the second derivative is negative, our first derivative's values are going down, and our original function is concave down. When is our original function concave down? Yes. Yes. Concave down. Just look. Concave down. When x is less than 1, negative infinity to 1. Okay? These are starting to get tricky. And next class it will be tricky because we'll combine the last two classes of understanding increasing, decreasing, concavity, concave up, concave down, being positive, being negative, all of that stuff. So we will combine them next class.